This is Calculus Part 3. Here is the y equals x to the 0.33333333 forever. In other words, x to the 1/3 power. That's this dotted line, which is a little higher than this dashed line, which was what we had a while ago. Y equals x to the 0.5, or x to the 1/2 power, or the square root of x. Okay, well, if you have x to the 1/2 times x to the 1/2, that equals x to the 1/2 plus 1/2, which equals x to the 1. And this x to the 0.333, well, that's the cubed root of x. X to the 1/2 is the square root of x. X to the 0.333 forever times x to the 0.333 times x to the 0.333 equals x to the 0.33333 plus 0.33333 plus 0.33333. In other words, x to the 1 power. Hence, x to the 0.33333 is the cube root of x. Okay, let's look at our curve. As usual, when x is 1, y is 1. Because the cube root of 1 is 1. 1 times 1 times 1 is 1. Okay, and the cube root, the square root of 1/2 was 0.707. Remember how we did that? We said 0.5 to the 0.5 equals 0.707106781. We just rounded off to 0.707. Kind of like when Panama military strongman General Manuel Noriega's mama used to call him for supper. She just called him Strong for short. Sometimes we have to abbreviate. But notice on this y equals x to the 1/3 curve that when x is 1/2, y is a little more than 0.707. It's 0.794. Let's see what 1/2 to the 1/3 power is. 0.5 to the 0.33333333333 equals 0.793700526. We'll just round it off to 0.794. Okay, so our little representative rectangle of area under this y equals x to the 1/3 curve, its area will be just like these other areas we've looked at, the integral of y dx. But y in this case is x to the 1/3 power, so the integral of y dx equals the integral of x to the 1/3 dx. And when we integrate that, we say 0.333333 plus 1 equals 1.333333. Then we slip that underneath here, and the integral of that dx equals that. If our limits of integration are from 0 to 1, we'll plug 1 in here. 1 times the cube root of 1 is 1, divided by 1 1/3 equals 3/3 over 4/3, minus 0 plugged into there. In other words, our answer is 3/4. That's the area under this curve between 0 and 1. We can use calculus to determine the volume of a cone. If you were given a choice of having an ice cream cone or half of an ice cream push-up, see, there's an ice cream cone, there's an ice cream push-up. They both have the same diameter or radius of circle at the top. They both have the same height. So what would you opt for, the cone or half of the push-up? Okay, you'll get more ice cream if you opt for half of the push-up. The volume of a cone is 1/3 of the volume of a cylinder with the same height and diameter. Let's figure out why. let's say we have a cone that has height equal to h. Okay, we'll call it capital H. Okay, and its radius is equal to r. So from there to there, we'll call that capital R. Okay, let's integrate the volumes of an infinite number of disks that are infinitely thin. Let me draw this a little bigger so we can see it. Yeah, here's a representative disk. Draw it a little bit of a side angle. Okay, does that look like a disk? Okay, we're going to integrate an infinite number of these disks all the way from the bottom point to the top. Our representative disk has a radius of r. We'll call it little r, okay, because this was big R, capital R, from here to there. So we'll call this lowercase r. It has a radius of r and a thickness of dh, or delta h, you can think of it that way. Okay, the area of this disk is pi r squared. Okay, the volume of this disk is pi r squared dh. Okay, because it's area times its height. Boy, I lost my place here. Our height from the bottom point, we'll call that lowercase h. You could say we're integrating from lowercase h equals 0 to capital H, which is the height of the whole cone. Okay, or you could say we're integrating from r equals 0, what it would be here, to r equals capital R. Each time we look at another disk a little higher than the previous disk, there's a change in radius. See, let's look at this disk here. I'll draw it out. Okay, and here's a disk a little bit lower than it is. Okay, there's a change in radius of that much, delta R or dr, whatever you want to call it, doesn't really matter. And there's also a change in height, delta H or dh, doesn't really matter what you call it. We've been through all that before in our earlier lessons. As you can see, our ratio of dr to dh is the same as our ratio of r to h, which is the same as our ratio of capital R to capital H. So let's just say dr over dh equals capital R over capital H. And you can flip this around and say dh over dr equals capital H over capital R. We just flipped our equation upside down. And it's mandatory that the side of the cone from the bottom tip to the top ring be straight so that R over H is always equal to capital R over capital H. Okay, so if dh over dr equals h over r, then running out of room here, dh equals h over r times dr. We just multiplied each side of this equation by dr and left us with dh over here equals h over r times dr. Let's call our little incremental unit of volume of this disk, let's call it dV, and it equals the area of the disk, which is pi r squared, this little r, times the thickness of the disk, which is dH, but since dH equals h over r dr, we can now say dV equals pi r squared, and instead of saying dH, we'll just say what dH is, h over r dr. So if we move all of our constants over to the left, we just rearrange this and we say dV equals capital H over capital R times pi times r squared dr. And when you're integrating these things, constants don't figure into the equation. The integral of r squared dr is r cubed over 3. So volume equals h over r times pi times r cubed over 3. But we're integrating from 0 to capital R. So we plug in capital R here for our r cubed spot. And we have V equals, let me erase some stuff we'll take up here in a minute. So now we plug capital R into the little r spot because that's our limit of integration. We have V equals capital H over capital R times pi times capital R cubed over 3 minus capital H over capital R times pi times 0 cubed over 3. Well, all this is 0, so we're left with this. So we have r cubed over r, so that gives us V equals capital H times pi times capital R squared over 3. And that's our formula for the volume of this cone. As you can see, the formula for the volume of this push-up, this cylinder, it would be the area of the circle on top and bottom, which is pi r squared, pi times capital R squared, times the height of it, capital H, and the volume of the cone is 1/3 of that. Now, back when we were integrating this, we just moved our capital H and capital R and our pi over to the left, because H, R, and pi are constants. Neither of them is a function of little r, which is what we were integrating. This is because neither H's value, capital R's value, nor pi's value is determined by lowercase r. H is going to be H no matter what little r is. Capital R is going to be capital R no matter what little r is. And the same can be said of pi. It's 3.141592 regardless of what little r is. When we integrate an equation, the constants just carry on into the integrated equation. In other words, they don't get raised to the next power and then divided by the new exponent.